This is Free Range Digital Design Foundation Modeling, Chapter 19. Topic of this chapter is parity checkers and parity generators. So very heavily centered about the notion of parity, which is not an overly complicated notion. Parity refers to the number of bits that are set in a given set of bits. Set means it's the bits of 1. So essentially that means you count up the number of ones in a set of bits. If that number of ones is odd, then those bits are said to exhibit odd parity, otherwise it's even. So even parity can be even number of bits set or no bit set. Primary use for this is in transmission protocols where checking the parity provides 1 bit of error detection. If the circuit detects an error, namely on the receiving end, the circuit can decide what to do. Either toss it out, try to correct it, ask for a resend. Different protocols have different ways to handle errors. What is notable about parity generation, parity, is the fact that it's our last iterative modular design device. And you'll see that in our examples. It's also another XOR-centered device. So the other iterative modular design devices were comparators and replicatory adders. Here is a parity checker generator, you'll see that. Lastly, when we derive the circuit for this, you'll see that it's uses XORs, XNORs. When we talk about a set of bits, it can either be a parallel combination, which means you have the whole set of bits at one time. Here we have 5 signals in this example. That's what we will be taking the parity of. We will count the number of ones that are set in those 5 bits. Other way to handle this is with a serial configuration. This is one signal, and what we're going to do is look at it at what we have here is 5 different times, and the values of that signal at those 5 different times represents the set of bits, and we can declare that either even or odd parity. We'll certainly be using both in our design process. This is the big data transmission example. We have something on the sending side that's going to transfer that data over a medium. Could be water, air, could be anything. And here we have the receiving side. So on the sending side, we have 3 bits of data, but what we want to do is add another bit, which will be the parity bit, and we're going to add that bit such that these 4 bits have a given parity, whether it be even or odd parity. Once again, we're going to assign this bit to ensure these 4 bits have even or odd parity. You're going to choose even or odd. You're not going to choose both in the same example. When I choose a given parity and I send it, the receiver expects that parity. If it gets that parity, it's highly probable that there was no error in transmission. Certainly, if it receives the wrong parity, there is an error somewhere in that transmission, and you have to decide what to do about that. So once again, the issue here, it's not simple sending the data, it's adding an extra bit. That extra bit gives me a little bit of flexibility in that I kind of know if the data made it here okay or not. Now the issue is if I get 2 errors in the data, parity is still going to be it's going to check out as okay, but in essence you made 2 errors in the transmission. This parity checker, this 1-bit parity checker, will not detect that. Then again, if you make 3 errors, it will detect that. The issue is the probability of making an error is generally pretty small. Probability of making 2 errors generally is much smaller because it's very close to multiplying those probabilities together, which makes it even smaller. This is our first example here. We are going to design a parity generator, and let's do it. So what we have here is three input bits, A, B, and C, and an output bit D. We want to make this even parity. We want to assign D such that A, B, C, and D have even parity. So this is going to be a brute force design approach problem. I'm going to assign D such that all the values in that row are even. To make that all the values in that row even, I assign D as 0 for that first row. Here I'm going to assign it a 1. So here there's a total of 0 ones. Here there's a total of 2 ones. And I'm going to do the same thing here. We got 2, and I'm going to put it there and a 2. I'm going to do the same thing here, so this is going to be 1. What's interesting about this is you can kind of see it here. This is an XOR function. This is an XNOR function. It's really evident that once we implement this circuit, you'll see some XNOR and XOR gates, or whatever it turns out to be. So let's do this. Now if I do the standard sum of products for the ones in the previous circuit, I get this equation. I know I need to factor some XORs out of it, so I'm just going to stare at it for a little bit. And what you see is this A bar is common to both these terms there, so I'm going to factor it out and get down to this line. Same with the last two terms. So what we see here is this here is an exclusive OR function. This here is an exclusive NOR function. I can factor that out a little bit. And lastly, what you see here is something complemented, something uncomplemented, something uncomplemented, and something complemented. So that too is a XOR function, and I can factor that out, and I end up with this circuit, or with this equation. And if I implement that, this is the final circuit. What I'm going to do is extend this example to 4 bits. What I'm going to do is assign this PR bit such that the A, B, C, D bits have even parity, and I can go through the same approach here. If you look at this, this is once again looks like a bunch of XORs and XNORs, so I end up with this equation after I factor it, and I'm going to end up with this circuit. The issue here is I added another variable, and that caused me to add another gate, and so that is the iterative modular design effect on these things. So this circuit is not the only way to implement this. There's actually a certain magic with XOR gates and XOR functions, however you want to put it, such that I can do this a little bit differently, so I'm going to do that real fast. So this circuit is another way to implement this circuit. They're functionally equivalent. The only difference between these two circuits is I have some parallel action going on in these two gates. Overall, there's just 2 levels on this. So this represents 1 level, this represents the 2nd level. Here I have actually 3 levels. So this gate, the circuit on the left here is going to be a little faster than this circuit here, but they are equivalent. You'll see that when you work with exclusive OR gates. Okay, so I have an example where I want to generate parity bit to indicate when 4 bits are, this is like a parity checker. I'm going to check to see when, if I send 4 bits, whether the parity is even or not. So this is going to be a circuit looks like this. There's my 4 bits. Even parity. So this is going to be the ugly equation here, so let's do it. So what this is saying is this even parity is these 4 bits even parity? Yes, no, no, yes. Okay, even. There's 2 bits set. Yes, no, no, yes. Even parity. Yes, no, no, yes. Even parity. Yes, no, no, yes. Okay, so in the end, I'm not gonna grind through these equations, but you can see these are all happen to be XOR gates, individual XOR terms in here. And if you were to actually implement this circuit and grind through the equations, or however you want to do it, it would kick out a circuit filled with XOR or XNOR gates. I can't remember which one on this one. If you ground through the equations, you could actually kick out the appropriate answer. This circuit here, this timing diagram, I have a parity generator circuit. Let's see, it's generating odd parity. Okay, so it's going to take these 4 inputs. It's going to add an extra bit, which is the parity bit, to ensure that it has odd parity. So let's go ahead and mark this off to make it clear. We do this. So this is 30011 4-bit input. That's even parity, so I have to add a 1. C1100, that's even parity. I got to add a 1. 40100, that's odd parity, so I don't add a 0. So this is a B. Right, 1011. Odd parity, don't need to do anything. 0, 1, 1, 1. Odd parity. 1, 1, 1, 0. Odd parity. 0, 0, 1, 0. It's odd parity. 0, 0, 1, 1. That's even parity, and so I need to add a 1. And this is C, which we've seen before. I need to add a 1 to that. Call it done. This is our foundation module for parity generator. Once again, it reads in the data bits and also kicks out a status bit. So this is kind of a parity generator and a parity checker at the same time. It's looking at the data bits and responding accordingly. So if it's generating parity, it assigns it one way. If it's checking parity, it will assign another way, depending on what problem you're doing. Okay, here's an example problem. What this problem does is, well, I don't know what it does, so let's generate a black box diagram for this. Circuit has one 8-bit input, so it has one 8-bit input. Okay, we'll call it A, and circuit blah 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 outputs either the value or the 2's complement of the value. So this is going to have an 8-bit output as well. And that's it. So the idea here is there's some conditions in here. So if the input is both even and has odd parity, then it outputs one thing, otherwise it outputs something else. That right there is a decision, and so that means the mux, there's going to be a mux on the output. 8 and val. Okay, so remember this val is that val. So what else do I have in this thing is a 2's complement circuit, so we'll just toss that in there since I don't have to draw it. This circuit is either going to output 2's complement or the original value, and here's our original value up here. Okay, so what else we need in this is, we're reading through this, where it has odd parity, even and odd parity. I know there's going to be an AND gate in there. I know that's going to control that mux, output that AND gate. And so what I need here is two things. I need odd parity. So I get to say odd parity checker. That's going to be one of these inputs here. So this circuit here means if the input is odd parity, this outputs a 1. The other part here is if the input value is even, that means I know a given value is even if the least significant bit is a 0. 0 being kind of negative logic, 0 is what I'm looking for, but for this AND gate here, I need to invert that. So if the LSB, I'm going to list up there, if LSB is a 0, it gets complemented and becomes a 1, and it makes this gate happen here. Remember, it's kind of a negative logic approach. Otherwise, if that bit's a 1, least significant bit's 1, it's an odd number gets, that 1 gets inverted to a 0, 0 gets fed to this AND gate, turns it off, it chooses this one, so I might as well go with that. 0, the input is even and has odd parity, the circuit outputs the input value, so this is a 1 and this is a 0 here. So I didn't really guess on that one, I looked back at the problem for this. So once again, what controls this circuit here is this control input on the mux, which is controlled by an internal signal. So this circuit has, okay, and we're going to call that done. So once again, we took advantage of the fact that we already designed a 2's complement box. We're just going to plop it down here. We already designed an odd parity checker. The problem is that I didn't really have to redesign those. So everything's good with this problem.